Consider a region S bounded by the square with vertices z equal to 1, I, -1, -I. Prove that any two points within the region S can be multiplied together to result in a complex number within S. So, after first reading this question, I think it's pretty obvious that you need to see what's going on here. You need a diagram to show you what the region S looks like. So here's our region S. It's the area within this square. Now the question isn't too specific about whether the actual border is included or not. I'm going to do it with the border included, but it should still work without the border included. Now what we're trying to do is we're trying to prove that if I take any two points within this square, within this border, and I multiply them together, I'll get another complex number that's still in this region S. So essentially what I'm doing, S is some set here, and what I'm trying to prove is that the set S is closed under the operation of multiplication. So how can I determine if that's going to be the case or not? I'm going to need a condition. I'm going to need a condition that will guarantee that I'm in the region S or in the set S, and I have to check that against the multiplication of two numbers within that region S. So the first part of the solution here is just going to be finding a condition, an equation, an inequality, probably because it's a region, an inequality that describes this region S. And we can do that fairly easily. It might not seem like the most obvious thing to start off with, but the actual maths of it is quite simple. What we would notice is that this square is actually comprised of four lines. There's a line in the first quadrant, a line in the second quadrant, a line in the third quadrant, and a line in the fourth quadrant. And I can use simple coordinate geometry to find the equation of each of those lines. And actually, if you're familiar with something known as the intercept form of a line, you'll get this very quickly. I'll just write it down here. The intercept form of a line says that if I have a line written in the form x on A plus y on B equal to 1, then I can read off the x-intercept and the y-intercept from this form. The x-intercept is precisely this denominator, it's just A, and the y-intercept is the denominator here, which is B. And this is going to make it very easy for us to find the equation of each of those lines in each of the four quadrants. So we'll start off with our first quadrant. In the first quadrant, and I'm going to specify here that this is when x is greater than or equal to 0 and y is greater than or equal to 0. And I'm including the boundary case, the equal to case, in the parts where the variable is greater than 0. And you'll see why in a moment. So in this region here, I've got this line, and the intercepts are x equal to 1 and y equal to 1. So I can easily write this as x divided by 1 and y divided by 1. So I get the line x plus y equal to 1. Now in the second quadrant, this is where x is less than 0 and y is greater than 0, greater than or equal to 0. What are my intercepts? My x-intercept is -1. My y-intercept is +1. So I'm going to have x divided by -1, or simply -x, plus y is equal to 1. In the third quadrant, this is where both x and y are less than 0. I have intercepts of -1 and -1, so I'll get -x minus y equal to 1. And then in my fourth quadrant, this is where x is greater than or equal to 0 and y is less than 0. I'll get x minus y equal to 1. Now, the reason that I've written all of these conditions for each of the quadrants is because now I'm going to use the absolute value function. And the absolute value function says that if I have the absolute value of a, that's equal to a when a is greater than or equal to 0, and that's equal to minus a when a is less than 0. And so now maybe it makes sense why I've chosen to include the equal to case with the greater than case, because that matches up with our definition of the absolute value. So here, because x is greater than or equal to 0, I can replace x with the absolute value of x. Same thing for y, I'll replace it with the absolute value of y. But here, when x is less than 0, I replace negative x with the absolute value of x. And in fact, what we're going to get for each of these equations in each quadrant, we'll end up with the absolute value of x plus the absolute value of y equal to 1. And that's true for all of the cases. So I'm going to go ahead and write that for each of them here. And you can check that really quickly for each of those quadrants. But the really cool thing is that this border, this square, you can draw a square in the plane with the equation the absolute value of x plus the absolute value of y is equal to 1. Now if I want the border plus all the region inside of it, then I don't take the equal to, I take less than or equal to equation. So I end up with the following. The set S can be written in the following way. It's all the complex numbers of the form x plus iy such that the absolute value of x plus the absolute value of y is less than or equal to 1. An alternative way that we can write this would be that we're taking all of the complex numbers z, where the absolute value of the real part, because that's all x is, it's just the real part of z, plus the absolute value of the imaginary part is less than or equal to 1. And so this now gives me a condition to check if something is in the set S or not. And so now we're ready to actually do the proof because we have a condition for being in that set S. So we'll start off by saying, let Z be equal to A plus IB and W be equal to C plus ID, where Z and W are both elements of S. And these are going to be the two that we multiply together and check if that resulting complex number is in the set S. Now, I'm just going to make a note that since these two complex numbers are in S, they satisfy that condition. So I know that the absolute value of A plus the absolute value of B is less than or equal to 1, and the absolute value of C plus the absolute value of D is also less than or equal to 1. Now we're going to check ZW. So what is ZW? ZW is A plus IB times C plus ID. When we expand that out, we'll get a real part of AC minus BD and an imaginary part of AD plus BC. Now I need to check this condition on the complex number of ZW. So I'm going to investigate the absolute value of the real part of ZW plus the absolute value of the imaginary part of ZW. What's that equal to? That's the absolute value of AC minus BD plus the absolute value of AD plus BC. By the triangle inequality, this is going to be less than or equal to the absolute value of AC plus the absolute value of BD. And then again, the triangle inequality, the absolute value of AD plus the absolute value of BC. Okay, let's say by triangle inequality, just to abbreviate it. Now, from my first and third term, I'm going to factor out an absolute value of A from those two terms, and then from the second and fourth term, I'm going to factor out an absolute value of B. So I have the absolute value of A times the absolute value of C plus the absolute value of D. And then factoring out the absolute value of B, I'm left with the absolute value of D plus the absolute value of C. And then this is a common factor between my two terms. I'll factor that out. What am I left with? The absolute value of A plus the absolute value of B times the absolute value of C plus the absolute value of D. And now we go back to what we wrote above. Each of those is less than or equal to 1. So this is less than or equal to 1 times 1, which equals 1. And so therefore, if Z and W are both in S, we end up with ZW also being in S because it has satisfied the condition of being in S. So we've shown that this set S is closed under the operation of multiplication. And that's the end of the question.